And thank you everybody for being here. It's really an amazing turnout. I'm surprised. I guess these online meetings have something good, which is people can attend. Um, so what I'm presenting is work that is a little bit different from the usual work in ICALP, in the sense that is more, I would say, applied. So, what is the purpose of what we have done? So, we're going to have a network or a graph in which every node is going to have a position in a metric space, and that's what we call a geometric graph. And in this graph, since every node has a position, very commonly nodes will be connected to the neighbors in that space. So it's a little bit like you did this graph and we were talking before, but in a very generic setting. And what we want is to add links. If there are already neighbors, short distance neighbors, probably there will be long distance links, or in general, there could be any link to this collection of nodes based on the geometric positions, in order to have a network that has small world properties. And that means that every pair of nodes is connected by a shortest path of very short distance. Ideally constant, but in general, something around polylogarithmic. So that is the first objective, is like building such a network. The second objective, the second problem, is how to have an efficient routing in this resulting network. Since we have positions in this metric space, very often the routing will use somehow the position or the geometry, the geography of the space. So as far as I can tell, the first attempts to build small world networks using a similar approach are by Watts and Strogratz, in which they were using as the basic graph to build upon a ring, in which they were adding chordal links. And in 2000, John Kleinberg showed that taking a torus, using a torus as a base underlying graph in which all nodes all the links in the torus are present, and adding a constant number as low as 1 long link chosen with a probability that is inversely proportional to the square of the distance. Essentially, you choose one node at random using as weight the inverse of the distance from the source to that particular node. Then what you get is a network in which the geographic greedy routing is able to find the target in log square steps on average. So other metric spaces can be considered, and in particular, there's been some wave of work using hyperbolic spaces. So in these spaces, what happens is like the nodes are embedded in a hyperbolic space, and they're usually linked randomly with some probability that depends on the distance in this space. So Krukov in 2010 showed how to build a network using this metric space that had small world properties. Then Bogunyarov showed that actually internet can be embedded in hyperbolic spaces, and links in the internet will be links in the hyperbolic links, and they have nice properties. Casañas et al. Showed how to build peer-to-peer overlays, and Robert Kleinberg showed that you could embed wireless networks into a hyperbolic space and use that solution or that embedding for efficient routing. In 2015, because this is the journal version, Brinkman et al. Proposed a network, a topology called geometric inhomogeneous random graphs. We are going to call them GIRG, which essentially the idea is to have all the good aspects of hyperbolic graphs without having to deal with the hyperbolic algebra and calculus. You don't have to deal with hyperbolic cosines and distances that are hyperbolic distances, which are somehow kind of difficult to deal with. Conceptually, what their network is mixing is the idea of Kleinberg on how to build a network from the torus, which is adding links that are whose probability of existing is inversely proportional to the distance, to a polynomial of distance. And another idea that was proposed by Chung and Lu, in which in order to build a small world network, what they do is they assign weights to nodes drawn from a power law distribution, and the probability is proportional. Probability of connecting to a given node is proportional to that weight. That naturally leads to hubs. Nodes that randomly chose high weights will be attractors of many links and will eventually, or it will naturally become hubs in a power law small world topology. So these two ideas are somewhat mixed in these geometric inhomogeneous random graphs by as follows. Essentially, initially, every node, you choose how many nodes you want to have. You place them in a uniformly random position in a geometric space, say two-dimensional, but in general, delta is the number of dimensions. For instance, a two-dimensional torus, a three-dimensional torus, or a three-dimensional Euclidean space. And as I was mentioning before, in Chung-Lu graphs, every node is going to choose a weight that is going to be drawn from a power law distribution. And then we're going to create links with a probability that essentially combines distance and weights. And if you forget about the theta and the mean, and we keep only the two central parts of this expression, essentially the first factor here is exactly or almost exactly the same factor that Kleinberg proposed, which is the inverse to the number of dimensions. And this is exactly what he was proposing of the distance. That was the weight that Kleinberg was assigning to a long distance link, is 1 divided by the distance to the number of, the dimension. And the other factor is essentially the Chung-Lu factor, which is I choose a node with, choosing a node, it depends on the weight of that particular node. So as you see, this product is combining both aspects. Both of them are raised to this alpha parameter, which is somehow tuning the sum, the whole choice. Okay. Notice, it's important to notice here is that alpha is the same in both factors. So essentially, what is happening is that you're gonna have a larger probability of choosing a node as your long distance neighbor if it's close to you, and therefore this first factor will be high, or it has a huge or a large weight. So it's combining the two aspects of these networks. Then, in another paper in POTSI 2017, the same authors proposed a routing technique in these networks. The routing essentially uses, again, the weight and the distance raised to the dimension as the essential aspects to use in order to choose what is the next hop towards the destination. So essentially, given a node, it chooses among the neighbors the neighbor whose function phi is largest, and that function phi is computed as shown here. Essentially, these two are, they're not constant, but they don't vary from one node to the other. So this is essentially the important part. What changes from one U to another U, from one neighbor to another neighbor. Okay. What happens here is that if the function phi doesn't increase by moving to a neighbor, then the routing fails. And what they proved is that routing fail with at most a constant factor, a constant probability. So a constant fraction of the routing of routing messages get to their destinations. So what do we do? What is our contribution? Our contribution is twofold. I hope that you don't find them like too trivial. The first one is in the construction aspect. So essentially what we do is we propose a model that is a generalization of this GIRC model. So we have two parameters, kappa and pi. Kappa is from Kleinberg, pi is from the power law. And essentially what we do is we, instead of, something that is slightly different from the GIRC is that we assume that we start from a complete torus, 2D or delta D torus, in which the short distance links are available. As GIRC does, we assign to every node a weight drawn from a power law with beta between 2 and 3. And we only choose one long distance neighbor. So essentially we're going to have, every node is going to have 4 local neighbors, and it's going to choose one long range neighbor. Of course, if it's chosen by others as their long range neighbor, those links will also be there. We assume that once a link is created, it's bidirectional. So it's not like you can only route in one direction, okay? And essentially, we use a probability that is very similar to the way the probability of GIRC works. Essentially, you have a factor here, which is very similar to the Kleinberg factor. You have a factor here, which is very similar to the Chun-Lu. We are removing some parameters and some extra factors that were not really necessary in our opinion. And the most important aspect is that we separate the exponent. We don't use a common alpha, but we use a kappa for the Kleinberg part and a pi for the Chun-Lu part. That means that appropriately choosing kappa and pi, we have essentially all possible choices. Making pi equal to 0 and using only k different from 0, what we have is Kleinberg networks. Choosing kappa equal to 0 and making pi different from 0, what you get is the Chun-Lu graphs. Making kappa equal to pi, we'll have is GIRC, essentially. And in general, kappa and pi don't need to be the same, so they could be arbitrary. So the second contribution is to propose another routing algorithm. Is again strongly inspired in the phi algorithm. We remove aspects from that function that, like the number of nodes or the minimum weight that appears in the network, which we believe are not essentially necessary. And we add this exponent k here, which is essentially just dependent on tau, in order to decrease or at least control the fail rate of the routing operations. Essentially, what we do is tau is a parameter that can be chosen, and what we can show is that given this expression of this phi, as soon as the message or the route is at a distance of at most tau from the destination, then using this function, the phi1 function that we describe here, guarantees that the route is not going to fail, meaning it's not going to happen that there is no neighbor closer to the destination whose value of tau1 is larger than the current value of tau1. That's what we guarantee. It could be like a mini contribution additional, is that in order to remove even further the probability of having failures in the routing, actually bringing it down to 0, we consider the possibility of having probabilistic routing. So we're going to have two versions. In our routing, we're going to have two versions. The tau det from deterministic, in which the function that I just showed is being used in order to decide what is the next neighbor to hop to or to jump to or to route to. But if there's no neighbor that increases with higher value of phi1, then the routing fails. In the randomized or probabilistic version, tau RW, what we just do is we follow a random walk in which the value of the phi1 functions is just the weight used to choose the next hop, and this guarantees that eventually all routing completes, and therefore there's no failure. For the routing algorithms, the objective is to minimize the average number of hops from source to destination. So we have evaluated these two techniques, the construction of the network and the algorithm for routing, simulating in a torus of size 101 by 101. We use, for the weights choice, we use a beta of 2.1, and in every scenario, we run 50,000 messages from source to destination. So we use 50,000 uniformly random chosen pairs, source destination, in order to evaluate the performance. Once the network has been built, so we are going to compare networks built with the algorithm from Gerg, and we're going to compare them with networks built with the kappa tau algorithm. And we're going to, in order to evaluate the routing, we're going to use the phi-based function of Gerg in a deterministic fashion, the tau and the geographic, so the one that always chooses the hop that gets closer to the destination. And we're going to also choose their probabilistic versions. So Gerg, although it was not proposed in the original paper, but we're going to also use a probabilistic version of the Gerg phi algorithm, and a geographic random walk in which we use, so I mean, it's actually a random walk, a classical random walk. So this shows and compares the degree distribution of a network built with Gerg and with the kappa pi technique. And as you see, both of them have a degree distribution and follows a power law. The exponent in the case of kappa pi in this case is a little bit higher, but it's essentially the same. So the average degree is a little bit higher. But it builds a network with a power law distribution of degrees, which is something that is usually assumed is required in order to have a small world network. Then when we run these 50,000 routing problems, we found, I mean, here what we have in this table, we're evaluating the topology obtained with GERC, and we are evaluating how different routing algorithms work in that topology. Because essentially all routing algorithms I was describing, they can be used in the topology of kappa pi, the kappa pi network, but they can also be evaluated in the GERC. So this is what we're doing here. So every pair, the first value of the pair is the average length that these uniformly chosen random pairs had in number of hops. And the second part is the fail ratio. As you see, only the deterministic algorithms fail, and random walks, or the probabilistic versions of the routing algorithms, don't fail. The smallest number of hops for every alpha, so every alpha means a different topology, are shown there for the deterministic option. And as you can see, 1.5 seems to be the one that has the smallest, although not a huge difference. With the tau deterministic. And the red one shows the values that minimize the failure. It's not by coincidence that the smallest failing ratio occurs for the largest value of tau, because tau is designed for that. Essentially, for tau equal 4 means that as soon as the routing is at a distance of at most 4 from the destination.
If you can finish in 1 minute at most, then we'll have 1 minute for questions.
Okay, let me quickly go ahead. So essentially, what we can observe is that the randomized versions have very similar number of hops on average, which means that by doing randomization, we're not losing too much. And well, out of the all the options, 1.5 is the best. When we go to the topology obtained with our method, what we observed is that, well, again, it is all that actually GERC phi gets better. But if we choose the best one, the one that gives better, I mean, the better results, and we go to compare, what we see is that red is the topology of GERC, blue is the topology that we propose, and you can also almost systematically see that the blue on the right is always smaller than the red, which means that KG tends to work better than GERC. Note that the scale on the left, on the y-axis, is logarithmic. And then if we go from deterministic, which is the one on top left, to probabilistic, what we see is that the difference, especially for the blue ones, with our topology, I mean, with our algorithm for routing, is not too bad. So the conclusion is that this topology and both pi, so kappa pi, KG, and GERC, they seem to be good alternatives to hyperbolic geometric graphs. The KG graphs that we have proposed seem to be working better than GERC, both in hops and in fail ratio. And what are we doing now? Well, we're running more simulations, more sizes of torus, because we only simulated 101 by 101. We're looking at other parameters like congestion. In fact, I didn't present them, but the topology that we have and the routing that we have has nice congestion properties. And we also want to add some analytical studies. So for instance, we would like to see whether we can find analytically the shortest path distribution in the topology that we're building, and evaluate what is going to be the stretch of the randomized and deterministic routing algorithm that we're proposing. So an extended abstract of this work has been published last year in NetEase, but we are working now in a more complete version of it. And if anybody's interested in maybe collaborating in the analytical aspects, that would be nice, because it's hard for us.